Yeah, I just didn't want to be cut, but I don't know how to do this. Somehow it's not, I don't see the little thing to get things out. Okay. No idea how to do this, but I think it's okay this way. Let me just put it here. Okay. Okay, so thank you. It's a real pleasure to be here today, of course, talking to all of you. I wish we could be together. Could be much more fun for sure. Oh, now it's a beer. Okay, good. So so today I will talk about dark matter effects, and I will try to tell you a little bit about dark matter effects on the early universe, and also one other example that has to do with the Muon g-2. And so, okay, so the outline of the talk is I will remind you a bit about the evidence of dark matter, although we already have Nicholas telling us a bit about that, the nature and mass range of dark matter candidates, the searches via astrophysical, cosmological, and terrestrial probes. Of course, it's very hard to look for what you don't know what it is. So this would be my introduction, and then I will jump into discussing two examples. One is light fermionic dark matter, and I will discuss a bit cosmological probes and maybe ask the question. We are working on that, on possible direct detection with new materials. And then the last part, more closer to my regular heart, is I will tell you a little bit about one example that is maybe less conventional in the sense that has light gauge xenons like xenos and leptons, for a SUSY WIMP that can be searched for, that can explain g-2. So we all know that there are galactic and cosmological observations that show that there is more matter in the universe than what we see. And in fact, in the 1970s, Vera Rubin with her colleagues started to measure how fast stars are moving in galaxies like the Milky Way as they orbit around the center of the galaxy. So she found that even the most distant stars in our galaxy, like here, are moving about as fast as our sun, which is around here, thus therefore contradicting standard Newtonian gravity predictions if we expect that all what it is the luminous matter. So it's clear that some invisible matter, that something that we don't see, is holding the universe together. Of course, nowadays we have many other ways of looking at dark matter in many scales and many times. Let me just do this. Okay, better. For example, gravitational lensing. So as Einstein told us long ago, space-time is distorted by the gravitational effect of matter, and that makes the light of distant objects move in curved lines, as the one we see here. And the effect of gravitational lensing is to distort the images of distant galaxies as we see it in our telescopes. So today we can use computers and make a map of all the mass, where all the mass must be in order to create these distortions. And this is the type of things we see. We see the galaxies that in this scale are like these spikes, and then we see a big mountain that is something else and is dark matter. And of course, we also know that about in 2004 or so, we saw the indications of the bullet cluster where two galaxies collided, as we see here, and so leaving behind this interacting gas while the dark matter of both galaxies pass through, and we see it here through gravitational lensing. Sorry. So, oops. Okay. Okay, good. No, sorry. Okay. So finally, we also have we can look at larger redshifts. For example, the cosmic microwave background, which was emitted 370,000 years ago, and so there we see things when the temperature of our universe was about 0.3 electron volt and atoms became stable for the first time. So the shape of this power spectrum, so we see here the CMB temperature fluctuations, and the shape of this power spectrum give us information about dark energy, about baryons, and also about dark matter at recombination time. And finally, we can see these nice simulations of the matter power spectrum that describes the density contrast of the universe as a function of a scale, correct? And what we see that we start in this nice movie from some redshift of order 30, when kind of the first stars started to form, and the universe was about 1% of its current age. And then we see how distributions appears to form. And we see in this nice plot of Scott some time ago, how doing embodied simulations, we observe that the red points are really error bars that we get from the slow digital sky survey. And the black line here is assuming that there is lambda CDM model, which assumes a standard general relativity and contains in this simulation 6 times more than ordinary baryon. And we see that this goes much better than a simulation with no dark matter or with some variations of the gravitational loss. Okay, so the point is, what do we know about dark matter? And the answer is very little. We know it couples gravitationally, the same as regular matter, but it's not baryonic. We know that it's the most abundant form of matter. It's interesting here, we know that it can be a part of an extended Higgs sector. So it can be just the dark matter in the Higgs sector, or it can be a very rich Higgs sector with some mediators that connect dark matter to us, or that connect those mediators with some portals like the Higgs or neutrinos or so. And we also know that dark matter can be particles or can be compact objects. And as we heard today from Nicholas, it can behave as like axions, then can be best described by wave-like disturbances. So the point here is that we have very little clue on the mass scales. So we have here a mass scale that is going from 10 to the minus 22 to 100 times solar masses. So the lower mass limit comes from the requirement that dark matter particles can have a sufficiently short de Broglie wavelength to form dwarf galaxies or galactic subhalos. And the upper limit is set by observational limits that we have not these very massive matches, and also from CMB anisotropies. What I will try to tell you today more is, here I said that there is some point which dark matter must be bosonic. It has to do with the Pauli exclusion principle, and this will be one of the points that I will come back in the rest of the talk for a while. So of course, this is very hard to look for dark matter with these big assumptions, with these big uncertainties. And in fact, as you all know, folding in assumptions about the evolution of dark matter density in the early universe can motivate more specific scales. So assumptions about the early universe, in particular, if we ask that the thermal dark matter is thermally produced, there is a large but much more constrained range of masses we can look for. And again, in the one part of my talk, I will be telling you about one example of WIMPs. So, so in some ways, I will look at some region here, and I will look at some region here. So if we can have weak standard model charges, as you know, and I think Nicholas talked about that, the dark matter can be part of an extended standard model sector, and this is what we usually call weakly interacting massive particles. But also it can, you know, in reality, so how much of a miracle the WIMP is really a bit debatable, in the sense that what we are really constraining, and we saw it also in Michelangelo's talk, is a ratio of the square coupling to the mass. And depending on how the mediator affects us, it will play a role there as well. So in reality, we can have, as I said, these WIMPs can be as low as 2 GeV or as large as 100 GeV. and this has to do with no overclosing the universe. But if we put, for example, a lighter mediator, then we can relax those bounds and get light dark matter, thermal dark matter that could be as low as 100 keV or of the order of the MeV. Also we know that it can have different type of properties with itself, and we try to explore that as well. And an interesting thing is that in reality, altogether, thermal equilibrium is easily realized in the standard model, which means for regions of couplings, such that it is easy to look for this thermal dark matter, to look for direct detection experiments like LHC or direct detection experiments underground. So moving forward, so over the next decade, there will be important advancement in astrophysical, cosmological, and terrestrial probes that will further investigate this whole idea of dark matter at many different scales. So as we know, the dark energy plus cold dark matter paradigm, the lambda CDM, has been extremely successful for predicting and explaining the large scale structure of the universe and its evolution with time. But the small scale structure needs to be better understood, and we hope that galactic scale observables will shed light on these small scale structures. And of course, I'm not going to get into a debate about missing satellites or Corcas problem or too big to fail. There are different options to improve those tensions, but still we need to understand better the small scale structure of the universe. In particular, observational constraints on subhalo masses will be powerful tests of dark sectors. And of course, for the second part of my talk, I will go back to the bread and butter of thinking that we can look, at dark matter in annihilation above ground. Okay, so thermal freeze out at the early universe, and then detect that annihilation products such as gamma rays or neutrinos or charged cosmic rays. This is one option. Then, of course, we have productions at colliders. As we were listening the talk before, we hope that we can create dark matter at the LHC or beyond and see it directly. And finally, we have a lot of, so we have a very strong program of direct detection where we are pushing the paradigm of thermal dark matter in many ways. And of course, there are other options of dark matter detection. So the many possible dark matter solutions, I was looking at this Nature article, and I realized that somehow the one case I will consider today that I didn't know where to put it, but it's not like bosons, so it's like fermions, so I put it here. Although has been discussed in the literature, it's not in this beautiful picture. So today I will look at two possibilities, light fermions, and discuss how light can light fermions be. And then I will tell you about one supersymmetric option. So motivated partly, as I said, by the null results in weak scale dark matter searches, and by these small scale tensions that we still don't have resolved completely, we would like to maybe look closer to the lambda CDM prediction. Okay, so let's move directly into the first part of my talk, that is the dark matter plus core dark matter. As I said, is a successful framework for a large scale structure, but we yet has to prove it in small length scales smaller than 1 megaparsec, and for you and me, 1 megaparsec is about 3 × 10⁻¹9 kilometers, and mass scales smaller than 10⁻11 solar masses. And so there, the theory faces challenges. And of course, there are, I think, very interesting things with cold dark matter, so-called at all redshifts, I mean, which is zero pressure, and where the dark matter energy density scales from today to later times as 1 plus c cube. So mainly just assuming that there is a well-defined density of matter per co-moving volume. And in that case, some of these small scale tensions could be due to baryonic physics that is still not well understood. And at least the experts tell me, including my own son, that they are not really nicely fully implemented in cosmological simulations. So then people have thought about warm dark matter, means producing the early universe with a temperature. Then there is some redshift, let's call it CT. CT is the redshift at which there is the transition between relativistic and non-relativistic dark matter. And so at this redshift, the pressure is proportional to 1/3 of the energy density. And this is obvious to see because, okay, this is the equation of a state, which is pressure over density. And if you look at this value of omega being 1/3 and you put it here, of course, you see that you can go from when the pressure is 0, so this goes like the density goes like cold dark matter. When the pressure is 1/3 of the density, this goes like 8⁻⁴, so it's relativistic matter, relativistic behavior. So of course, people have worked a lot on looking at what are the properties of warm dark matter, and it has to be cold enough for structures to form. And basically, that puts at this CT range that the mass or the temperature of this warm dark matter has to be above 5.3 keV. It's also possible to have other options, mixed dark matter with, well, obviously, cold dark matter plus warm dark matter components, or other scenarios that have different equations of a state. So today, what I would like to talk about is what we call cosmologically degenerate fermions, and show readily that fermionic dark matter cannot be as cold as being non-relativistic at early times. And let me tell you what I mean with that. So in the case of light fermions, fermions or bosons, if we want to have basically that the de Broglie length has to be larger than the separation between two particles, because at that point is the point when dark matter behaves like a wave. So in order to avoid that, we have a bound on dark matter, thinking about the velocity of dark matter in the Milky Way and the density of dark matter in the Milky Way, that is a bound of around 10 electron volt. So just above 10 electron volt, in order not to be behaving as a wave. But now when we have fermions, then this adds on the fact that due to the Pauli exclusion principle, there is a fermion momentum, and the fermion momentum here is related to the number density, which is of course related to the energy density of dark matter that we are seeing. And so this is a Fermi momentum, and this in fact implies that I need some large Fermi momentum, and this Fermi momentum, which evolves like the number density, and we know that the number density, if we think that the number of particles per co-moving volume is a constant, correct, then the number density is higher at higher redshift. And if that happens, then we know that at some redshift, that is the one that we call already CT, this Fermi momentum is of the order of the mass of the fermion, and this is when the particle becomes relativistic. And one can, this is a back of the envelope calculation, but one can do a calculation, very careful, considering the actual momentum distribution of a fermion, and one can obtain that this Fermi momentum of order of m psi, defining this relativistic variation boundary, is a good estimate. So what this means is that fermionic dark matter, which becomes relativistic at any redshift that are larger than this CT, can be and then relativistic even if there is absence of that certain temperature. So at this moment, I am thinking that the temperature of the dark matter, which decouples, and I will go into that assumptions in a second, is basically zero. So the temperature of the dark matter of the dark sector has decoupled basically at some time at the beginning of BBN, and it remains with a fixed co-moving number until today. Okay, so as I said, we assume terminally cold dark matter, which means that the kinetic energy is from purely degenerate pressure. And I will go back to that because this is going to give us the weakest bounds on the mass of the dark matter fermion, and therefore the most conservative. So what we do here, so we know about this Fermi momentum, and of course this will change as a function of the redshift, correct? And we know how this number density evolves with time, with redshift. So using these two equations, one can, and given the fact that we know what it is the present day energy density, okay, related to the number density today, here I put some number of flavors which one can set to 1 or not, and that will just rescale the results. So then we can define what is the moment or the redshift at which dark matter pass from being relativistic to non-relativistic. Of course, you already can guess this is very important because when we think about contributions to delta and effective, that will play the crucial role. So we can do this calculation, and this is the result I have here. And this is, if you like, sorry, you cannot see there because it's this thing is here, but this is the paper which is put out where all these calculations are done very carefully if you want to go and read more about it. So, so we compute in this way based on today's energy density, what is the time or the redshift that with dark matter goes from being relativistic to non-relativistic as a function of the mass of the dark matter and the fraction of dark matter energy density that we have today. And this is interesting because most studies in the literature have not considered that there could be a lower amount of dark matter and that in the way of these fermions, and that we have, of course, we know all that we can have many components of dark matter, but this study is going to consider this fraction of dark energy density at current times. And this is the value we just put that the fermion has 2 degrees of freedom, and we just consider 1 flavor. So, with this equation, we can say which is CT as a function of psi and m psi. And these are different values that I will go back to them in a moment. So this is the matter radiation equivalence, which is about 3,300, and this is what is called high K Z, which is basically the first times when the smallest clumps are starting to be formed, that it will be the seeds of the structure formation much later on. So from here, we can actually compute what would be the contribution to delta and effective for this dark matter. And let me tell you just in a few words, this is a bit more of lengthy calculation, but the energy density of the dark matter in the relativistic regime, we are going to characterize it by its equivalent number of effective neutrinos degrees of freedom. And of course, we need to be careful when we look at the energy density, that when we are thinking between going to from the matter to the radiation era, of course, the redshifts go differently. But altogether, after some calculations, you can say that for any z that is when the dark matter is relativistic, the contribution for delta and effective is given by this expression, where here this dependence of 1 of CT is coming from this equation here. Okay, and of course here this is this value kappa. So this is the number of neutrinos, and this is just the ratio that takes into account the fact that there is a difference between the neutrino temperature and the plasma photon temperature when things evolves, because it plus and minus goes into photons and change and reheats the photons. So
Marcela, you have 5 minutes.
Oh God, that's bad. Okay. So what I'm doing. So in that case, I will skip over this and tell you that for this value of delta and effective, I will look at what I get from Big Bang nucleosynthesis and cosmic microwave background, and I will put a bound from my multi-parameter extensions of lambda CDM. So I will look at delta and effective being below 0.5 or below 0.1. And the other thing that I will do is that the other issue that is important is look at the suppression of gravitational clustering. So if a fraction of this today called dark matter is relativistic, as I said, at these values of 10 to the 7, then these small clumps does not occur at early times. And that, of course, is not good. So what happens is that then the small clumps does not occur at early times, and then basically this slow down the overall growth of matter density perturbations. And so we can constrain these from Lama alpha forest data and counting Milky Way satellite galaxies to determine the subhalo mass function. So what we do now in the last minutes I have is, we calculate the linear power spectrum as a function of the mass and the fraction. We normalize out to what would be the power spectrum for cold dark matter, and then we compute what is called the transfer matrix as a function of wave number. And let me just show the results here. So the results we get are we compare this power spectrum. We use this class package, and so we compare this power spectrum in this area with a warm dark matter with a mass 5.3 keV, and we look considering these bounds from Lima alpha and subhalo mass functions that I can go into detail if you ask me later. So we can see that we can fit different contributions of mass values and fractions, and we can go, for example, here as low as masses of 10 eV with 4% of dark matter. And so here the smallest wave number implies, so the smallest wave number means that this is the value where the CT starts occurring, and so start disturbing the fermions become to contribute because they are relativistic. Okay, so going back to the fermionic parameter space, so this is kind of the result. We see that we can, if we have the whole dark matter being given by this fermionic dark matter, then we found that the mass of the fermion has to be above 2 keV, and this is due to the impact of degeneracy pressure on structure formation in the early universe. We can actually constrain fractions as low here as 3% for values of the mass of the electron of the order or below 0.1 electron volt, and this is because these degenerate fermions add non-negligible to the total energy density in the form of radiation, and that, of course, disturbs our power spectrum. Also here, we put delta N effective larger than 0.5 or 0.1. Let's look at 0.5, and we see that still with those constraints, which are the most strong constraints for very low values of the masses, we can have sensitivity to constrain fractions of dark matter as small as sorry, this is -5, 2 times 10 to the -5, no, for masses that are as low as 0.1 MeV. So this is all excluded, and this is the area that is interesting. And before, because I want to say one word about SUSY, let me just show the last plot, and don't go into all this, but I'm happy to tell you about it, that we have looked at the Fermi velocity of the degenerate fermions and how it will modify Milky Way dark matter phase space density. And what we found is that in this area of parameter space, basically there's no accumulation, so they will just be larger than B escape, and the density would be very small, and so it's not an interesting area. In this area, the degenerate fermions will basically behave today, so basically local implications today will behave like cold dark matter. But in this area in between is interesting because one can have smaller overdensities or higher velocities, so we can really change things in the way that could make this interesting region available at values of at new type of detectors, like, for example, some type of new type of crystals that could look and be sensitive at very high velocity distributions of the dark matter. So this is kind of a summary. So I let you there, and let me just in the last 2 minutes tell you that we all have heard about the g-2, and I think that's exciting, very exciting. We are trying to find new physics that could, new particles that could be interacting with the muon and telling us about this difference in between the experimental and the standard model results that are of the 4.2 sigma. And of course, today I would like to tell you a bit about SUSY. This is a paper I did very long ago, and actually with Carlos and Jan. And in supersymmetry, in g-2, you have 2 main interactions. And the interesting thing is that the dark matter particle plays an essential role in these g-2 supersymmetric explanations. And I invite you to read my front page Scientific American article of October that talks about this, not about SUSY so much as about the g-2 results and all about it. But let me just show maybe the last thing is that there is an interesting region of parameter space, and what you have to look here, where we have looked at bounds from direct detection, indirect detection, and LHC bounds, and you see that there are these regions that are interesting for negative values of n1 times mu, or positive ones. For positive ones, basically you have the large mu solution that is the regular solution, but there are solutions in these areas, the darkest area here and the darkest area here, where you can explain g-2 with a light Bino-like dark matter. You can have the right relic density through co-annihilation with staus or muons, or with charginos, and you can be in the region where you're close to some blind spots, so that you are okay for cross sections, and so to avoid direct detection experiments. And I would say, because, and this is my last slide, if you look at that, I don't like you to pay a lot of attention, but if you look at these particle masses all here, for example, this is annihilation with the muons, so this muon mass is very close to the dark matter mass. This is annihilation with the staus, so the stau mass is very close to the dark matter mass. But what you see here is that your spectrum is very light, And there is good prospects to probe these benchmarks at the LHC and in direct detection experiments. And then, unlike the large mu region for supersymmetry that maybe is never proven, this is a region of supersymmetry where if you explain G-2, you will be able to see new particles at different experiments in the next decade. Thank you.
Thank you, Marcela. Very nice talk.
Okay.
Lots of information. Are there any yes? Are there any questions or comments for Marcela? Yes, Rogerio, go ahead.
So I have a simple question about the light fermion part, which you probably mentioned, but I didn't get it. How do you produce them in the early universe?
Well, that is the UV completion. It can come from. I didn't mention that because we have two possible solutions in the paper, but we are working on this UV completion more. So it could be like resonant production coming from some scalars. It could be for actually it is possible that we have basically a population of these particles from that form like composite states and at early times in some some composite states at early times with some abelian theories, and there are different possibilities, but we are working on the UV completion of the model. So I don't have a full answer to you. There are some back of the envelope calculations that could get these fermions, as I said, from resonant scalar production or from coming from making bound states.
Okay, thank you, Marcela.
Okay, Nicolas, go ahead.
Okay, thanks, Marcela, for the nice talk. So I have a question from the beginning when you were talking about the degenerate fermions. I think it was a slide called or titled Cosmologically Degenerate Fermions.
Yes.
So you had a statement that confused me. Could you please go back?
Let me look. So I put it. I'm sorry that this every time I touch this gets stuck. Sorry about that. Let me just put this small so you can see.
Exactly that one.
Yeah. Sorry. Yes. Please go ahead.
What was it? Okay. Yeah. You say relativity radiation at G higher than GT, even in the absence of dark sector temperature. I mean, why?
Say it again. I'm sorry, Nicolas.
So that sentence, relativity radiation at G bigger than
GT.
this
is because sorry. This is because we are basically thinking that what I say, that the fixed comoving number has been fixed for some mechanism at the beginning of BBN and until today. So basically what it means is that we can analyze this with zero temperature, and the only kinetic energy it has is coming from the Fermi pressure, from the Fermi momentum. So that's what it says, in the absence of dark sector temperature. All the analysis we have done is for zero temperature for the dark fermions. Okay, and that's the interesting thing, that the whole issue that they are relativistic at some redshift is because independent of having zero temperature, they have this Fermi pressure. This is very important. Thank you for asking, correct? So because you cannot put more than if you have just one flavor, okay, you are going to occupy all the possible states. You don't have so many states to occupy up to the lowest energy state, and so you have this Fermi degenerate pressure or Fermi momentum, and when this Fermi momentum is of the order of the mass of the fermion, then is when these particles become relativistic. So this will happen at some at some redshift, correct, because the Fermi pressure is proportional to the number density to the 1/3, and this number density is higher as higher redshifts here, correct? So at higher redshifts, this PF is going to increase, and it will increase unto a moment when this particle becomes relativistic, which is this thing here. Is that clear? Or
okay? Yes, I see. Thanks.
Okay.
Okay, thank you. Are there any other questions or comments for Marcela? Okay, if not, I'll ask you a very general question, Marcela. Recently, there was a paper, a PRL, on relativistic Muon. So this is a more general question. As you know, one of the big issues for Muon has been always the CMB. And they claim in this new paper to have solved that. So I just wanted to know your opinion, general opinion on Muon and the alternatives to dark matter as matter.
Yeah, I have to confess, I don't know that paper. And of course, this is a very old plot, what I'm putting here from 2011. But I think that, this is the power spectrum. So it's part of the information we are getting also from CMB. Mm-hmm. So again, as I said, as you know, I'm not a cosmologist by education. I am learning from my son, Sebastian, who is becoming a cosmologist by education. So the best thing of this talk is that I discuss a lot with him about a lot of questions I have about how to look at this, and he was very keen in explaining it to me. But I think that, maybe you can help the rotational curves, for example, but I doubt that this power spectrum, that here is so different. Okay, look at the difference in the power mm-hmm. spectrum from Muon. But I don't want to disvalue this PRL that I have not seen, and I don't even know who are the authors. So I right. look at it.
But in more general terms, so not thinking about this paper in specific, but about the fact that it may be a combination of things, in the sense that we don't know everything about gravity.
Yeah, I would bet that different types of gravity, although some are very smart, are not going to solve the problem that we have with with the missing.
That's pretty clear. That's pretty clear. Thank you, Marcela.
But details are in the the devil is in the details, of course. But
of course,
I think that we need to understand better this small scale behavior of the universe. And I was, that's the area where I would be more interested in understanding what we can do with, different type of dark matter. Rather, that is the area where I'm interested in at this moment, basically.
Thank you, Marcela. Okay, let's thank Marcela for her nice talk and comments. And now it's turn for Diego Restrepo. So if you can share your screen, Diego.